Thank you, John. So just before we get started, thank you very much to over 70 people who responded to this challenge before the Monday night cutoff. That made it very hard to pick winners. I could only pick 2. So first of all, many of you gave very nice solutions. Thank you. And since I had to pick 2, let me describe very briefly the exercise and then show you the 2 who have some wonderful iPads that I'm told run great Google search and Microsoft Office as well. The idea is I want to write a case-insensitive string class. It's a straw man example. There are other ways you could do it. But if I wanted this kind of type, how many comparison operators would I have to write today in C++ 17, the latest modern stuff we just shipped, in order to provide comparisons between CIString and CIString, CIString char star, C-style strings, and of course that has to be symmetric. And even the CIString, I would like to be symmetric because you want conversions on both sides. The answer is, 12 ought to do it. No, wait, 18 ought to do it. And how many of you have enjoyed writing code like this? Sorry, how many of you have written code like this? Way more hands, only a couple of enjoyers. So thank you to, and could we invite up Manuel Bergler and Ben Dean? Can you give them a hand, please, wherever you are? Come on right up. Manuel, I enjoyed that you used string view, so you could actually take more than const char star, which was needed. And I like that you showed an if-deft preferred way I do it in production code for real, but here's what you're probably looking for. I like that. Both were actually good answers. And also, Ben, I picked you before I realized you were a fellow speaker, so oh well. But that's okay because we prefer neither way. And I liked that you also had a very nice solution that avoided extra conversion operators, allocations. You didn't just convert to a CIString and compare those. And you referred to my paper about this spaceship operator to simplify this. So that was really good. So that was a good awareness. So thank you, both of you. Enjoy your iPads. And thank you again to Stevens Capital Management for providing those, as well as other iPads for some of the other questions in the contest from the speakers this year. Now, this is actually semi-related to the talk. It has actually nothing to do technically with the talk, but it has a lot to do in principle. So the reason I picked this example was I have a completely different proposal that's currently making its way through committee. It builds on the work of many others, including Bjarne Strustrup and others who have done other proposals in the area of comparisons, Lawrence Crowell, many more. And this proposal is currently on its way through. It's been approved by the evolution groups, and so it should go into wording review, and hopefully, if nothing blows up, it'll be in C++20 draft in the next meeting or two. The idea is that we invent something that other languages already have, but the idea of a three-way comparison operator. Other languages have the three-way comparison spaceship operator, because that's what it looks like, Darth Vader's TIE fighter. But it's something that even in C we've had. strcomp does this. So we've had comp functions, and if you're familiar with Perl, Python, some others, they have similar things under different names. The idea, if this proposal is accepted, is that instead of writing those 18 functions, you write 2. Notice they are members. They don't need to be non-member friends to get conversions and to get symmetry. You say, I want to compare against another CIString. By the way, that returns a weak ordering. That means it's an ordering, so I generate all 6 others, not just equality, inequality. And I actually have more information because it says what kind of ordering it is, which we do not have expressed in code today. Oh, and by the way, there's another one, because I also want to compare against C-style strings. That could be even better as a string view, as several of you in your solutions pointed out. And it also returns a weak ordering. And so the nice thing about this, all I say is weak ordering. That means I generate 6, or in the second case, 12. The effect of 12 functions doesn't actually generate the functions. It just makes those operators available in your code, and they get rewritten to calls to the spaceship operator. It's efficient because in the previous solution I showed, you might have noticed that a common thing we do is we implement 4 of the operators in terms of equals and less than, which is inefficient because on a common, if you do, for instance, less than equals in terms of less than or equals, turns out you have to traverse the common prefix, the equal prefix, twice, depending on how you code. And so that's undesirable. This is guaranteed to be single pass. It's guaranteed to be symmetric, documents that there's a weak order. And there's a lot less boilerplate to write. The key is the idea is to allow people to express intent directly. So this has nothing to do with this talk. And yes, it looks like it's a TIE fighter, Vader's in particular, but I choose the Falcon, so sue me. It also kind of is that shape if you squint just right. But the reason this was a nice segue here is because the rest of this talk, especially the part about metaclasses, I'll give an overview of related features first as well, like the spaceship operator, is about making C++ code simpler. We're adding features to the language, so the language is growing incrementally, but C++ code should be simpler to write. How? By letting programmers state their intent more directly instead of circuitously. Say things that in fact we're already writing, so we're not inventing new requirements. These are things we are already doing, it's just hard. They do it by generating things for you transparently, so we're going to have some way of letting the programmer see what's going on when that's necessary, for example, in debugging. And that means tools are necessary to make sure these features not only work to write code once, but make sure that code that you write is also continues to be easy to debug, to maintain as you release it over time. So with that, let me switch to the main topic for today, which is thoughts on generative C++. And again, the goal is to make C++ more powerful, which means we're adding capabilities, but for C++ code to be simpler. It is possible, if you do that right, to actually simplify the language additively, which it seems like an oxymoron, but you do it by adding abstractions. The way that I've gone through this exercise, so for the last two and a half years in particular, I've decided to focus on spending the time I have to write standards proposals from the 100 things we could write and add to the language, specifically to things that might simplify C++ code. And that was a very general and very broad exercise. And from that, I'm now taking some things and as appropriate, one at a time, and bringing them to the committee. The spaceship operator was a target of opportunity. The committee was already talking about that. The design I had in my pocket was already informed by that discussion, Lawrence Krall and others. And since, after rejecting it for C++ 17, they continued to talk about it, I said, well, fine, let's have a proposal and do it right. And see if that's something that could get consensus, and happily it has, building on other people's work as well. But the whole exercise to find out ways to simplify C++ has been driven by one thing that helps to keep on course. And I think it's important to have help, at least I need help, to stay on course from all the wonderful gadgety features that we could imagine to ones that really simplify code. And the way that I've chosen to do it is to look for people digging with spoons. How many of you have written template metaprograms? On purpose. No, okay, that was just a joke. How many of you like template metaprograms because they let you express important things, but wish you could do it without writing the template metaprogram? Almost as many hands. That's what the committee as a whole is working toward and what this talk is about. So if you find something that people are already doing with inadequate tools that express things indirectly, like, look, templates are Turing complete. I'll bet we can compute some stuff at compile time with that. And they're willing to endure that much pain to get that effect, that tells you there's a market for shovels. And it tells you that, yes, you are not inventing some new feature that's taking C++ and turning it into a different language, taking it into a different direction. This is something C++ programmers already do. It's just hard. And that's important because it demonstrates the market need. It also demonstrates it really is C++. It's what we are already doing. So a good tool should make those things easier and more things possible. So we observe people digging with the spoon of template metaprogramming to compute values and types at compile time. So we've been adding constexpr functions. We're doing much more of that I'll talk about to have first-class compile time programming. Express your intent more directly, what you're already doing. We observe that people are creating interface definition languages, side languages and compilers that know about things like properties or the com classes or Qt classes. And they do this because they need to express something that they can't express in the language. Is there a way to let them express that in the language so that you don't need the side compilers, you don't need the non-portable extensions? Again, something that people are already doing, usually multiple ways, multiple times. Can we bring that into C++ more directly? Everything I'm going to talk about is under construction. What we are going to talk about is, it's always exciting stuff, especially at the beginning, where you're liable to say, oh great, can I use this like in my project in 6 months? No, probably not. Even the earliest parts of this are early. Reflection is one of the earliest that is currently actively undergoing wording review, so that has a good chance of being in C++ 20, perhaps, we'll have to see. But the rest is longer term. But look at this as an arc of where we are going that should reassure us that C++ is going in a good direction that will help us, and expect also that much of the syntax I'm going to show you is going to change. It's just straw man syntax. Some of the concepts may get tweaked. But let's see how far we can go to replacing some spoons with shovels in our language. Most of the talk is going to be on the bottom thing, metaclasses, but I want to take a few minutes first to talk about the foundation that's being built and give you some references to papers where you can find out more about that, especially for reflection, compile time programming, and injection. So let's focus on just that part for now as the foundational work that is already in progress. Reflection is at the most advanced stage so far in committee. The other two are still being more incubated. And then see what we can then do to build on those things, assuming they exist. So first, reflection. Thank you to many people, but 3 of the main people who've been working on this for a long time, Matus, Axel, David, several of you are here in the room. Thank you to your companies, GlobalLogic, CERN, Bloomberg, and the other companies that send people to committee meetings, help them write papers, do implementations, and you can find much of what they've written here. If you're looking for information, here are cherry-picking a few of the papers these people recommend you read. So thank you again for your review on these slides as well. But if you want to find out more, thank you to all these people. Let's give them a hand. So really briefly, what's the idea? The syntax may change, but think, okay, prefix dollar to some expression, some type, gives you a const PR value of meta : type. So it might be a meta : function, or a meta : variable, or a meta : type that represents a class. And then you can iterate over its member functions and its data members, things like that. Query things like their types, their constness of parameters, and in general, ask for information about the program that you can then query and find out more about, and then do things with. We don't currently have proposals, we do have some early thinking, but proposals to reflect on statements and expressions, so the bodies of functions, but declarations are well along. The idea is that we can apply this reflection in ordinary code, where it's just another read-only value, which the compiler may or may not need to even bake into the object file if it inlines the results. But you can't take its address, because it may or may not be in the object file. That's why it's a PR value, a pure temporary. But in compile time code, it's just an ordinary variable, an ordinary temporary. And I'll discuss compile time code in a moment. But there's the nutshell summary. I'm going to show the bike shedding thing only once, but assume that this appears on every single slide for the rest of the talk. Syntax may change. It may be prefix dollar expression. There are lots of concerns about that, including interaction with existing code generation tools that already stake a solid claim on the dollar symbol. So we may not want to escape that all the time. We may want reflexpr with angle brackets or with round brackets. We may want some underbars. Who knows? As long as I can spell it some reasonable way, I'm a happy camper. For the purposes of today, I'll use prefix dollar. Again, all of this is subject to change. So what can I do with this? Well, a very simple example is, let's say I have an enumeration and I just want to iterate over all the enumerator values. So you might want to say, reflect on my enum type, and if that's a type that has, in this case, if we expose those enumerators as variables, or the reflection might return an actual enumerator's function, then I just go through and print each of their names. And so this gives me the ability to look at my type and then do something, compute something based on what that type is. So I'm really getting a view like a compiler into that type. One of the nice things about this, by the way, is as soon as you show the very first example like this, and by the way, yes, you could constrain type name using concepts in C++20. You can constrain that to just enumerators, things like that, so it only compiles, it's only available for enumerations. But one of the nice things as soon as you do this is you get all the other benefits that we have in C++. For example, when are templates instantiated? When they're used. We don't go stamp out a million templates for all the types you might decide to write in the future, just the ones you ask for. So when you ask for print strings of state, if that is the only instance of print strings, the use of print strings in your program, that is the only enumeration whose values are stored in your object file, or in fact, an optimizer could optimize that away and not store them, but just store only the labels, only the text, for example. But all this work is done at compile time, only in calling programs that actually use it. So I could ship these 4 lines as a header-only library, and in every translation unit for now and in the future it's used, it would be instantiated only for the enumerations that that program actually asks about, and only in that program, which is nice and efficient. This is dear to our hearts because what do we believe in more than anything else in C++? Don't pay for what you don't use. This is that, and we just naturally get to take advantage of those things. So once we've looked at reflection, thanks again to those people, and now let's move to compile time code that can use reflection, because that's where you really start to get the benefit of it. And in particular, there are many, many more committee members I could thank, but in particular, David van der Voorde of EDG, Louis Dion at Amazon, Anthony Polukin at Yandex. I know at least Louis is in the room, and many others. Here are some of their papers. Thank you to them and many more for working on this and helping us get what I'm about to show on the next slides. But let's give them a round of applause as well. This is hard work. I'll tell you, these papers do not write themselves. And it takes a lot of discipline, time, and expertise to really follow through on a proposal. So where are we today? Well, thanks to, in particular, Gabi Dos-Reis, who I believe is in the audience today, we have constexpr in C++11. We have more constexpr in C++14. What, you want more than one return statement? Oh, all right, you can do that in 14, but not 11. You want a loop? Oh, you can do that now where you couldn't before. You want lambdas? You want if constexpr? Well, now other people get into the fray, and so thank you to Gabi, Faisal, and Vila in particular, but also to many others for getting us more and more constexpr in the language. So Vila in particular for if constexpr, Faisal for generic lambdas, and for constexpr lambdas. But would you like more? Yes. Good, because you're going to get it whether you really want it or not. So thanks to some of those same people, Anthony, David, we're now looking at papers post C++17 to make virtually all of the algorithms in the standard library constexpr. Think about what that means. Why shouldn't I find diff at compile time instead of writing my recursive functional style template metaprogram? Well then, if I have an algorithm I want a container, because I can do all this with arrays, fixed size arrays, wouldn't vector be nice? Could I have something vector-like? Well, it turns out there are proposals about that. And the question is, how far can you go? And earlier this year at C++ Now, and 48 hours ago at this very conference, the answer was, thanks to Ben also, who just got an iPad. It wasn't for that, but thank you, Ben and Jason. Well, let's just make everything constexpr. So we'll see how far down that road we go. But we're seeing much, much more already. What more can we do? Right now, when we have constexpr functions, they may run at compile time or may not. And if we want to have an actual piece of code that is guaranteed to run at compile time, that is one of the current proposals I cited earlier. The idea of a constexpr block is the current thinking, which I can put at statement scope, so inside a function body. I could put it class scope, at namespace scope. Now I start being able to write imperative code in a lot more places. But again, is this something weird and not C++? Am I turning C++ into Lisp? Not that that would be a bad thing. Actually, it would be, because the design goals are different. No, again, remember, this is letting us write more directly the things we are already writing. And that helps us to have that guiding star to make sure, yeah, we're not just doing some weird other thing in a big left turn or right turn. This is still C++, just easier. And C++, just easier, is something we can all get behind, I think. So the idea of in my normal code, I can have a constexpr block, which means that IDEs can highlight it like this, or I can see it visually very clearly in my code where my compile time code runs. Helps me to distinguish it between those two boxes on the left and right, the normal code versus the compile time code. Now, the next question, as soon as you say that, and it's by these same people, of course, are saying, well, but wait, if I now have a constexpr block of compile time code within normal code, what if I want to go the other way? I want to write normal code, generate it from within a constexpr block. How many of you were already thinking that? Yes. How many of you are now thinking about it? Yeah, so the idea here is we have an injection operator. And the current proposal in PO 633 and related papers is the arrow sign. There might be some ambiguities there, so a word like inject might be better. Again, the syntax is all straw man. But the idea is that I could now, in my compile time computation, say, okay, I now want to inject a declaration into the surrounding code. By default into the enclosing scope, or perhaps into a certain nested outer class or namespace. One place where this shows up is in the very simple example we just saw, where instead of printing every enumerator value of an enumeration, what if we just want to print the actual name in source code of the enumerator at runtime of a given enumerator value? So then I can write a toString function for an enumerator. Again, I can constrain it with concepts. And now notice that there's a switch statement inside which is a constexpr block, which all it's doing is for every variable injects a case statement. So once the compile time code is run, what do you have? Switch, case, 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 case. Could you have written that by hand? Sure. I won't even ask for the show of hands because I know many of you have. Then what happens when you add an enumerator? Right. What happens when you change an enumerator value? You know, it's hard to keep these things in sync because as soon as you say something twice, you will lie now or in the future. I mean, we just can't help it. Authors of fiction novels can't even get the middle initial of their main character straight from page 52 to page 123, right? We will lie. This will lie less because it asks what is the truth. There's one source of truth, which is the type system. And man, if you got to pick a source of truth, type system is the one you want to pick. And then ask it, what is the truth about, say, this enumerator? And now I can use this with the various enumerations I have. And again, just like any other template, we instantiate it only in the programs that actually use it at compile time and only for the idioms that are actually queried, which is a nice feature to have. Much better than just injecting all enumerator names and baking them into your exe just in case they might be used, which is what we resort to today because it's hard to be more precise about these things. As soon as I talk about injection, like this might have come up before, but especially with injection, the concern about injection is, but what about being able to debug this? What about being able to maintain it? Because if we go back to here, I just showed you how to automate writing all your case labels. How many of you thought that was pretty nice? How many of you worried about that you can't see that code? Good, that's a healthy reaction, almost as many hands. You should worry about that. Just like in many other places in the language, even back to C and any language with abstractions already hides information. So let's see what we do about it, because we'll do the same thing here. So we already do things that are less transparent. There's two arguments to be made here as to why we should just go forward and pursue this direction, even though there is a transparency issue. The first thing is, remember, you're going to get sick and tired of me saying this, but it's so important. We are already doing this. This is making code easier to write that we are already doing in nasty ways, like template metaprogramming. And even if this is hard to debug, it will be less bad than the things we are doing now. How many of you have debugged template metaprograms? How many of you, by the way, just curious, how many of you are in shops that do not allow non-library use of template metaprograms in production code? Like, besides something you got like from Boost, they just don't allow you to write template metaprograms in production code. A few. Well, because of debuggability, maintainability, those kinds of things. So it will be at least less bad, even if we do nothing in tools. But we already have cases like this. For instance, the compiler-generated functions. Let's say you have a class type with 10 members, but I want to use compiler-generated destructor, assignment, copy. How many of you have already wished you could step into in the debugger and see what was going on in each of those? How many of you actually have a tool that does that? Much smaller number. They exist. But yours, I know, is your own research project. So yes, exactly, Peter. You have so few hands that I can actually see individual faces to see what tools they're using. So we already have this problem, and yet nobody is burned or bent out of shape saying, oh, we shouldn't have special member functions, they're too scary. We like them, they're convenient. We could still have better tooling than we even have today. So let me just take a moment before we switch to metaclasses for the rest of the talk to just talk about this general principle, because I think it's worth, I added these slides last night because this has already come up multiple times in the last 2 days at this conference, including at the panel that we had on Monday night, in hallway discussions. And so let me just address one thing that I think is important to remember when we talk about language abstractions and especially tooling. By definition, abstractions are hiders. They hide stuff. It's what they're for. If they didn't do that, they would be useless. They would not have the value that they have. So it's not a problem, it's the point. Now, having said that, you could use this to gloss over many things that should never be put into languages. I'll talk about that a little at the end. But abstractions are good. We cannot build our civilization without abstraction. We are so deep in the layers of software that we write. We could never have scaled to what we have today without lots and lots of abstractions. And where C++ shines is it makes those abstraction layers thinner, more efficient, which is why C++ will always have a future, because we'll always be building bigger and deeper things, where thinness of the layer matters. That's where we shine. But let's just go back to the 70s. Abstractions have always needed tool support. So variables hide their values. So in a tool, yes, you could do printf style debugging, then you're just writing your own tool. But any IDE will give you a watch window. Any debugger will give you a watch window so you can see the value. Why did you need that? Because the variable x nicely abstracts away its current value. So you can just talk about the value in the abstract, which is wonderful. We've been doing this since the 50s. It's really important. But even that is an abstraction. A function hides code. Notice the word hide appears all over the place. Now, that's okay. We just want to think about the documented semantics and not worry about the how it does the work. But sometimes you want to step into, especially when you're debugging your own functions in a cascade. So you need go to definition. You need step into in your debugger. Pointers hide in directions. You need visualizers that let you see what the data structure actually looks like. Include hides dependencies, because include files could include other files. So build systems need to be aware of that. That's the first thing. The second thing is they need to see when the file timestamp has been updated, usually, unless you're in a database repo or something like that, so that they can say, this changed, and therefore, based on the dependency graph, I will go and build all these other things. But we're not scared of these things. We'd like to do better at some of them, like include files, but we're not scared of them. They're very useful, even though they do require build support. C++ has been very successful, even in its early years, for classes. Guess what? They hide code and data. It's the whole point. We have built a whole generation of software tools on classes in many languages because it's good they abstract behavior. They encapsulate behavior, which means they hide code and data, which means you need most of what we just talked about in your tools. Overloads hide static polymorphism. I could have said templates, but we always go for that one. Let's say overloads, because that's another form people don't often think about. That means we need better warning and error messages. as if you've had compilers early on that didn't have them, you know, because you want to know, oh, I couldn't call this, but here were the candidates, right? That's important to know. Virtual functions, they hide dynamic polymorphism. Again, a different kind of tool support. So that's C++ up to about 17, 18 years ago. In C++ 17, I could mention a few more things, but along the way we've added more constexpr. Constexpr functions hide computations that can be done at compile time. So with constexpr functions today, because they could be compile time or runtime, you can fake it out by executing them as if at runtime. But you basically are starting to see a need for compile time debug support. Why? Because that's where you're running your code. If constexpr, more of that. We hide whether code even has to compile. So just like you have your macro ndebug and your IDE often grays out the code that isn't actually being built, which is actually a useful thing to see, I would expect tools to do the same thing with if constexpr. Because whatever appears in there isn't going to be compiled in an if constexpr false block. So again, we need tool support. I'm spending so much time, 3-4 minutes, talking about this because this is not a new problem, and it's important to emphasize it's not a new problem. So that, oh, darn, I've run out of space. Let's fix that. If we now go into the future, modules. I have heard, even at this conference, some angsting about, well, modules, are fundamentally different? Are they going to need more build system support? Sure, half of that build system support is what we already have, to know when a file's touched. Yeah, we do that with headers. We can see when a compiled module has been touched. Yes, we need to look inside modules to see which modules this module transitively uses, yeah, which is not that different from what we do for headers as well. Does the build system need to be aware of it? Absolutely. But notice again, like the header, the module, in a better way, is an abstraction. It hides stuff. This is the point of modules. It bundles stuff up. It doesn't mean you can't look at it. You can go in and look at it, but it gives you an abstraction. And so we need tool support for that. This is not surprising. Compile time variables, compile time functions. Just like regular variables and functions, we need tool support for those, but they need to be able to run at compile time. And when we talk about injection, now this brings us all the way back to our previous slide. When we talk about injection and metaclasses, which depend on compile time computation and injection, we are generating stuff. So we need to visualize that. And I'll show an example as we go. But remember the thing at the very top. Don't lose sight of the title of this slide. Abstractions are hiders. This is a feature, not a bug. It's the point. And it does mean they need tool support. Now, I promise at the end of this slide to make one caveat. Good abstractions also need to be toolable. This is a two-way contract. Please do not use everything I just said to justify some awful language feature design that is not a cohesive abstraction, that is undisciplined, and say, yeah, tools should just make it better. Like, for instance, with if constexpr, the standards committee was very careful to make sure that you couldn't just generate arbitrary source text, like, let's generate half a class and then stop. Or generate the back end of a class, close the current class, open another one, and do something else in a single if constexpr block. That's not scoped. It's not nested. So it was very careful to make sure that an if constexpr block was a scope, and we had very clear rules about the scope. Guess what? That makes it more toolable. So please do not use the, you're going to have to write tools anyway. It's those lazy tool writers. It's their job. Don't use that as an excuse for a bad language feature. A good abstraction, however, does have a responsibility to also answer, is this going to be write-only code, or is it going to be code I can debug and maintain? So it has to be toolable. And then we can reasonably say, okay, let's make sure we build the tools for that. And the closer we can show how it's similar to things we are already doing in tools, the better. So having said that, let's now move to the back part of the talk, where I'm going to assume all of those things exist. And the question that I was interested in, and the piece of my broader simplifying C++ exploration that I'm bringing forward here, is how can we get rid of things like compile time code by convention, by tools that weren't designed for it, like template metaprogramming? Just because they happen to be Turing complete doesn't mean you have to Turing complete them. And how can we use that to makes C++ code simpler, again, focusing on things we already are doing, just harder. So the idea of metaclasses is covered in my paper, P0707. Many reviewers, thank you to them, and a special thanks to Andrew Sutton. Where are you, Andrew? Can you yell or wave? Yo, in the back. Thank you, Andrew, because besides being Mr. Concepts Implementer, having written the concepts implementation in GCC, he is now actively doing the metaclasses implementation in Clang. So thank you very much to all the reviewers and to Andrew for all their help on everything I'm about to present. I'll give you links at the end to a couple of talks Andrew is giving about the implementation details. They're not so much about the use, but about the implementation details this afternoon and tomorrow morning. Look for those in your schedule too, if you care about the implementation detail side of things. I know there are a lot of Clang hackers in the room, so you'll find that interesting. But the most important shout out I want to give is to somebody who I think is not currently in the room because he had to take a flight right now. But I want to especially acknowledge Bjarne Strustrup. Nothing I am about to tell you would be possible if he had not held the line in a principled, strong way on a unified type system in C++. Let me talk about that for a second. So here's a movie that's playing everywhere in theaters. Okay, I'm not going to talk about James and the Giant Peach. I'm going to talk about Bjarne and the Unified Universe, because when we take a look at the whole universe of all these C++ types that we can express, there are so many. We talk about value types. They're the ones that are favored by default with the special member functions that get generated by the language. But we have plain old data structs. They're blessed with a name in the standard, although you can't actually quite see them in source code as clearly. But people write com classes. They write functors, callable types, a very different thing, but it's still just a class. A single inheritance-based class obeys different rules. We write down what the rules are in English, but it's just a class. C++ does not have a separate interface concept for that. We write expression templates, properties, Corba interfaces, any variant, so sum types, product types. It is fundamentally a strength of C++ that every single one of these can be expressed as a class, that we have not bifurcated the type system. And nothing I'm about to say would be possible without that. The trouble is that right now we're writing all of these things and much more, but we're doing it by convention. So some of these are documented in the core guidelines as to how you should write them, or in Scott's or my books or others. And we describe them in English instead of as code. Can we do better? So the goal of metaclasses in a nutshell is to give a name. A name is a word of power if it's compilable. To give a name to a specific subset of the universe of classes that have common characteristics. What common characteristics? I want to express those using compile time code, all the stuff we just had a very brief overview of a moment ago. And the goal is to make classes easier to write, because I don't have to remember English rules. I don't have to override the universal defaults for what gets generated for me to make them appropriate for my kind of class. In fact, every single metaclass that we should write, and this is important especially to committee members who worry about opt-in. We often talk about new features and, oh, can we make them retroactive to old code? No, we want people to opt in so they know what they're getting. Every metaclass you write is a single word that is a bundle of opt-ins. That is a powerful thing to be able to write and customize yourself, because you are saying, I want this. And now a lot of the stress and anxiety about providing useful things by default, but what if they weren't needed, melts away because the user asked for it. So a very important contribution, I hope, of metaclasses is to have a generalized way of writing an opt-in. To say, I want this. And you know what? Once you say you want it, then we can go wild and help you. It's about helping the developer express intent. Let's see the nutshell example. I want to write a metaclass as a very, very simple thing. This is the current vision. We're trying it and evolving it, and I'm sure it's going to mature, and especially with feedback from the committee who saw this for the first time a couple of months ago in July. And we're going to continue to improve this. This is a multi-year effort. No, it's not in C++20. My goodness. No, this is incubating still. It's not a first proposal to get to evolution yet. It's incubating, but I hope it's promising. So everything may change, but the current idea is it's a custom transformation from the source code you write to an ordinary class definition. Now, let me explain what I mean by that, because we already have it, except I can't write it myself. I have to be a compiler writer today or a standards proposal writer. In the language today, I write class point int x comma y, or I write struct my class :base void f. I have all sorts of language rules that apply. Class point automatically gets x and y be private. So I didn't write an access specifier, but I get one, as if I had written it, right? We know these are the rules. Oh, by the way, I didn't say anything that would prevent generating the special member function, so I get a default constructor, a destructor, a copy constructor, a copy assignment operator, a move constructor, a move assignment operator for free. This is great. Unless you didn't want them, but here I do. So this is great, and it's done for me. I didn't have to write all that stuff. This is a feature, not a bug. With my class, I inherit publicly by default from the base because I said struct. And notice that the function f is virtual if it happens to have a signature, the same signature virtual in the base. So I didn't write virtual here, but I implicitly get virtual because I inherited from the base class. Like or hate that feature, it can be useful, and it is something the language already does for us. So when you think of this, here's what I wrote in source, and here's the actual definition of the type. You can think of it as if the compiler executed this italicized pseudocode for each member. If there's no access specifier, then, if they said class, make it private. Otherwise, if they said struct, make it public. Oh, by the way, for every function, if it's virtual in the base class, and it's not defined as virtual here, then make it virtual. If it's not virtual in the base class, but they said override here, then emit an error. You wrote a function that says override, but it does not actually override a function in the base class, right? And so on. All of these rules in the middle are already things we use every day. They're in the standard, they're in compilers. Today they are written as standardese, and they are implemented by compiler writers. I like standardese, but only a few dozen people in the world can write it. I'm not always one of them. I rely on people like Jens and Richard. So do most of the committee for core wording standardese. I like compiler writers, but there are only a few hundred of them in the world. What I would like to do is to be able to have more people in a disciplined way, not in a free-range, all rules are off Wild West way, but in a disciplined way, be able to write just that code and give it a name. So is it true that C++'s defaults are all wrong? People say this sometimes. And they're right when they're writing a kind of class that wasn't intended as the common case when we picked the default. So really the main problem with C++'s defaults, in many cases, is that, especially the class-based ones that I just described in the middle there, it's one size fits all. The class, like every single class, has this same set of rules and defaults. Even if it's a functor, or a com-based class, or a plain old data struct, I couldn't say those things, and that means I have to equals default or equals delete the things that did or didn't get generated that I actually wanted when the single heuristic for the whole universe of classes guessed wrong, right? So if you can only pick one rule for everyone in a diverse universe, it's going to be wrong a lot of the time. That's why we have equals default, equals delete for the purposes of opting in and out. So instead, the key question is, what if you could write your own code here and give a name to a group of defaults and behaviors? And people have sometimes said, what kind of code is this? It's so strange. It's code. Put it in a library. Put it in a namespace. Do all the things we already do with code. Share it on GitHub, then compile it with somebody else's compiler that supports this language feature. That's the intention. Again, I want to be clear about what we are proposing and what we aren't proposing. Only participating in interpreting the source code definition that you wrote and what gets generated as the definition, the one definition of the type. We are not trying to make this a mutable language. That would be madness, or at least if it's not, I don't want to explore, and I'm not interested in going there and seeing whether it's really as crazy as it looks. I could get what I want without that, so I'm not interested in exploring that. I am also supremely uninterested in violating the ODR. The one definition rule is great. C++ benefits strongly from it. Bjarne was very wise to insist on that from the early days of C++. Now it is paying off in spades with new features like modules that really rely on the one definition rule. So when we generate something, it's just a class. What we generated from is just the normal C++ grammar, except that instead of the word class, I could put in something more specific. That's the only grammar change. Other than that, I want to leave the language alone and let it evolve orthogonally. So give a name to a group of related classes that have common behavior. Give it a single hook that is a translation customization from source to definition. And I hope that this can replace many uses, along with the other features that we saw, of template metaprogramming, macros, and non-portable language extensions. It's not an open grammar, not a way to violate the ODR, and it is not specific to object orientation or virtual functions, even though that's the first example I'll show. Most of the examples I already cited have nothing to do with OO, but C++ does do OO, and this is C++, so you can use it for that too. So the current idea is that I can write, instead of a class, a dollar class, that's the current syntax for metaclass, and it contains the rules as a constexpr block of compile time code of the things to apply to whatever the source code was that I wrote. And then I can apply it in the place of the word class to say interface shape, for example, instead of class shape. And if my dollar class interface had all the rules to require that functions be public and virtual, make them that way by default, make sure there's no data, then when I say interface shape, I am opting in. See, there's that big red opt-in button that says, I want all of that, and all I had to write was one word. That's convenient. It's important to opt-in be explicit, but we also want to make it convenient. The best way you can do that is to get people a way to write a customized opt-in. And then if I say interface shape, then I get those defaults. My functions are public and virtual by default. I can't write anything other than that. And the typical things that metaclasses are used for in our experiments so far have been to enforce rules, to provide defaults, and to provide generated functions. Many of the things already done in the language with just the word class. So here's an example of how we write code today and how I would like to be able to write it in the future. Today we write interfaces just fine. We call them abstract base classes, ABCs. They even have a cutesy name because notice we're trying to give them a name, even though I can't say the name in code yet today. The name reminds us of the pattern we learned as English, and that maybe a linter will help us with. But I just remember I make every single function public, I write virtual, I write equals 0, I have a virtual destructor, let's make it no except while we're at it, and then I am very careful not to write a data member, a non-public function, a non-virtual function, and I have to make sure that my future self who's maintaining this, or their successor, keeps the rule. So today, what happens if under maintenance I actually accidentally add a data member on the left-hand side? Code compiles and runs. It's not what I wanted though. It may mess with the size and alignment of things in a way I hadn't expected. Or it may just violate the fact that if I have a non-virtual function, that may violate semantics. But I don't have a way to write that unless I want to resort to writing lots of static asserts, and nobody does that with reflection. The proposed way is to write interface shape and then write your functions. Notice I did not write public because it's public by default. I did not write virtual because it's virtual by default. And I could enforce that I didn't write any data members, copy, move, that kind of thing. Here is how it looks in code. And again, Standard disclaimer, this is strawman syntax. So my $class interface first declares the destructor, and then has this constexpr block I just showed you before. So it's building on these other proposals that we hope to get anyway, and says, oh, how can I use them? Now I want to write compile time code, which requires that reflect on interface, or reflect on myself is the current syntax for that I have no data members. Variables is empty. Otherwise, I will emit a compile time error which can be integrated with the compiler's native error handling and controlled by the same switches. You are writing a compiler extension here. Interfaces may not contain data members. For every function, require that it's not copy or move. Otherwise, say, interfaces may not copy or move. Consider a virtual clone. You could be creative. This is a good thing. If it doesn't have an access specifier, make it public, and then require that it's public, and make it pure virtual. So then, when I say interface shape, that metaprogram runs on the things that I wrote, the declarations in the scope of shape. That's the idea. One of the nice things I think about this is I didn't write any standard E's. No standard E's was harmed, no core wording was harmed in the making of this code, once we have the feature. I can write this and put it in GitHub and have you try it out and debug it for me. I can use debugging tools. I can write unit tests for this, which I cannot write for standard E's. I can do this on my own on a weekend much faster than writing a paper and going to a committee meeting and then trying to get it through evolution and core, and then wait for my compiler to implement it years later. And my claim, my hope, but I'll say claim because I believe I have evidence that this is going to pan out, is that it is without loss of usability, expressiveness, error message quality, or performance, even compared to other languages that build the feature in as a first-class entity. Now, that's rainbows and pixie dust. Like, that's the holy grail if we could do that. I have some reason to think that we can achieve that. So if we compare to the C# language, here is how the interface concept is implemented in the current C# specification. That's actually a zoomed out version of the C# specification. It's about 18 pages of English, so standard use for us. The proposed is on the right-hand side, which is about 10 lines of unit testable code that I can ship on GitHub in a library in proposed C++. That's already some benefit. But what about the use case? So in C# and Java, I can write interface shape, int area, void, scale by double factor. The proposal, as I'm showing it here, has exactly all of that, except this is C++, so you have to write a semicolon at the end of the class. It's okay, we can get over the semicolon. Oh, and by the way, you can write things like const, which you can't write, or at least not with the same meaning, in other languages. So you get to use whatever C++'s rich language features are already. And let me just show the difference in philosophy, because in Java and C# the idea is, well, we bake something in as a language feature. That way it gets first-class support, it's going to be efficient. And we do that with interface, we do that with lock, or synchronized in Java, which is a language feature that lets you do local locking. But that's not who we are as C++ users and language authors. We want to write general things, such as lockguard in the bottom right, where I can have almost the same convenient syntax. Notice this is C++ 17. I didn't even have to write lockguard angle mutex angle. I can get just about the same convenience, but the right-hand side is just as usable, and it's more flexible because you can't do timed locks on the left-hand side. You can, and if it wasn't in the standard, you could easily write your own type to do a timed lock with backoff on the right-hand side and get the same usability and the same experience. Because we're library writers. We have a language that is arguably the best in the world for writing libraries, and we want to make that even more powerful. So let me just demonstrate that real quick. Here is C#. Is that all right if I show some C#? Okay. Nervous laughter. Better laughter. That sounded more relaxed. So here I have interface shape, and I can write this in C# today. And if I say, for instance, let's say I make that private. Oh, notice I got a red squiggle. And so it says, oh, in shape area, the modifier private is not valid for this item. Okay, I can't have a private member function, a private method in C#. What if I added a data member? Oh, it doesn't like that either. If I hover over, it says, interfaces cannot contain fields, which is C#E's for non-static data members. The word fields might be better, but hey, we've doubled down on non-static data members. Non-static data members it is. They can have fields. Now, what I'd like to be able to do in C++ is write something like very much like what I just showed on the screen. So here is basically the same thing I showed on the screen. In this version of the prototype compiler, there's still a ... on the 4. That's going to go away as this goes through committee and we follow the guidance of the committee. Other than that, I think it's the same as what I just showed you. And also there's a way that you can debug. You can actually output what gets generated. Now I'm asking for something that doesn't exist yet, so let me just, I love this part, pardon me, cut and paste C# into C++ because of course that's a thing we always are able to do today, right? And then you'll notice, oh, it doesn't compile. Why? Somebody already noticed? This is C++, so we got to write that semicolon. And then it compiles. And compiler debug shows you, in this case, what it generated. So if you were doing this at the command line, you could have that print out. Notice that debug statement is running at compile time in this constexpr block, and you can see what it generated. This is important because if you remember nothing else from this talk, remember that these things need to be toolable. Right there in the bottom right of that demo is the thing that tools need to build so you can step into. That's it right there. This is not just demoware. There's a reason I put this demo in the talk, just to show you, look, we can see what we got. But that's also the first step of toolability, is to be able to see what we've got, and then IDEs can build from there. But we already have that today. So thank you again, Andrew, for doing this implementation so far, and we continue to make more of the examples in the paperwork. Only a few do so far. But remember I said with equal efficiency compared to other languages that do this as a built-in language feature. Well, this is all at compile time, so the runtime efficiency is the same. I just built a C++ class. Same as any other C++ class, I just wrote it more conveniently, right? But what about diagnostic quality, I said? Well, let's try some of these same things. Let's try int OI, because I have keyboard bounce. Error, interfaces may not contain data members. Okay, let's compare that to C#, where if I'd written, what was the, oh, let's say OI, to be the same. Interfaces cannot contain fields. Yeah, that's a wash. I'll say we have equal diagnostics here. Fields might be still a shorter name, but just saying. But now what if I wrote, oh yeah, in C#, what if I made this private? I have a private method, and then I see the modifier private is not valid for this item. What's an item? This is the kind of generic error message that you get, or partway generic, when you're a compiler writer who has to write just a general error message framework. It's not specific to a particular thing, although it could be in this case, because interface is baked into the language, but it's just using a general thing saying, can't use this modifier in this context. So to save space, they're using reusing an error message. So private is specific, this item is generic. So it's a halfway generic error message. Whereas here, what's the natural thing I get? When I write private, I get error, interface functions must be public. Now why? This is important. It's not only that I can get better diagnostics, but the example I just showed you, because C# could easily have done the same thing. The Visual Studio folks looking at this on YouTube will say, oh yeah, we can make that better, check it in the next version of open.net or whatever has the fix and has an equal error message. But this is what you get by default for language baked-in features, because compiler writers write generic, or by default write very general grammar-based diagnostics. This is a grammar-based diagnostic. When we write diagnostics with metaclasses, we are thinking about the metaclass that we are writing. We naturally write this because it's what we're thinking. It's the rule we're implementing as we go. So I think that not only am I hopeful that, as I claimed here, that we have the same usability, expressiveness, and even diagnostics as other languages that build many of these things in as direct compiler-supported, plumbed-in features. I think that not only can you get parity, but it's just naturally you get better diagnostics because you are already thinking specifically about the thing that you are authoring now, the abstraction that I'm having here. So that's one example. Here's another example, a value type, a regular type. Then we can argue over a beer whether regular types include comparison operators or not. Let's embrace them for this slide. Today in C++17, I write a bunch of stuff, and I have to reinstate my default constructor. Notice that very first red line. Why do I have to reinstate it? Equals default. I see in the front row, it's like, oh yeah. Right, because it was suppressed by who? By point int. You wrote a constructor, so we didn't give you a default one. You can always reinstate it with equals default. That's what we teach people today. It's true, it works. And I have to write my comparisons. I make them friends because it's easier than just declaring them and then defining them out of line, but I want to just write them here, and this way I get conversions on both sides as well if point is convertible to from some other type, and I write my comparisons. The proposal is that I can just write, that I would be able to write a value metaclass that does those things, and I'll show it on the next slide, the next slides. Value point would say, oh, data members, those are private by default, because that's what we tell people to do anyway. So let's use the opportunity. Make data members private by default. Functions public by default. Oh, and a value always has a default constructor, because that's part of being a regular type, so I don't need to reinstate it. So on the left-hand side, I had to write point paren equals default, semicolon, to reinstate it. That's an opt-in. It would be tempting, but wrong, to say that the opt-in evaporates on the right-hand side. No, the opt-in is folded into the word value. And that value is the same opt-in for, yes, I do want a default constructor, as it is for, yes, I want the comparison functions. And yes, I want copy construction, copy assignment, move construction, move assignment. And a non-virtual destructor, which I can enforce for a value, and I can't get it wrong even under maintenance. Now, what if under maintenance I write value point, and today I require that it can't have a virtual function or a virtual destructor, because that's not what values are, right? You don't want to slice them. And you would only use virtual if you're doing something like that, or protected, have a protected member. What if under maintenance I did want to add that? Well, if I did it by accident, as soon as I I maintain the right-hand side and I add a virtual function or a protected member, I would get an error. That doesn't mean I can't do it. It just means I can't do it silently. I can write a protected function or a virtual function on point, but to do it, I will have to change its category from value to something else. And this is nothing but goodness, because it means I can't do it silently by default, make the mistake. But if I really meant to do it, I can say it clearly, concisely, and explicitly without a lot of boilerplate. So having a single word of power to opt into a group of defaults is, I think, really, really important. And it all comes down to letting the programmer express intent. Yes, I just started this talk by mentioning P0515, the spaceship operator. Even with the spaceship operator, so C++17 plus that proposal would be even shorter, but you'd still have the opt-in for the default constructor and so forth. So I still think, even with that, there's value in the spaceship operator that is orthogonal, and metaclasses give you further value on top of it that's, again, independent. Here's what the implementation would look like. I won't go through it in detail, but you'll notice that at the top, you get all your basic functions, and we can actually go through, we require that they be defaulted. You could actually write code that just tests for them and injects them if they're not there. Then in the constexpr block, we make sure that all the variables, if they have don't have an access specifier, are made private. And if for every function, if there's no access specifier, it's public. And we make sure it's not protected, virtual, or a destructor with a nice high-quality error message. And then we compose metaclass value from, it is a basic value, which has all those things, and ordered, which I'm not showing, but it's the one that generates you the comparison functions today. And again, with spaceship operator, you would just use the spaceship operator inside ordered. And then I can write value point, as shown before, and I can write code that does equality. That works, it's fine. I can write set of point, which requires less than, and it works. And all I wrote was value point, int, and a constructor. And I've opted in to all of that power. Now, here's another thing we do in C++17. For those of you who can't read in the front row, it's class pair. It is, I believe, from the current working draft, or maybe a couple of working drafts old, the definition of class pair, because pair is such a simple class, it couldn't possibly be hard to write. So what kind of class is pair? What can't I do with it? Read the code, read CPP reference. I would very much like to be able to write literal value pair, T1 first, T2 second. I'm not showing the code for that. The code for literal value is the one example I use that I don't show the code in the paper, but presumably by now you can see, I already have an inkling, here's how I would write that code, because I would want to generate all the things on the left-hand side, if they're not written already. This was actually a challenge that I put to several C++ committee members about 5 years ago, when we were just kept on adding stuff to pair. Turns out pair is really hard. Marshall, are you in the audience somewhere? Marshall, am I roughly quoting you correctly when I said was it pair or was it variant that's right at the edge of what we know how to do? Oh, it was tuple. Okay, which is more like pair. Excellent. And oh yes. So the answer was yes. And if hearing that from one of the main authors of the Clang standard library implementation worries you, we understand that we want to make these things easier. A simple thing should be simple, as Bjarne rightly says. This is simple. We should be able to make it simple and write literal value that we can reuse for pair and for tuple, and define pair and tuple in this way. This is the only proposal I've seen that would let me actually write pair as T1 first, T2 second. I think this is a very good litmus test, at least for me, a litmus test on are we on the right track? Because here's an example of stuff we're doing today, even though it's hard. And we'd like to do it more directly. This is a poster child example of stuff we need to do today, and we're digging with a spoon. Can we find the right kind of shovel that can make this clearer to do? Here's another example, enums. Enums are baked into the language. Imagine that we had a basic enum metaclass. Again, I'm following the standard library convention for extracting common stuff into a basic underscore prefixed type. And notice it is a value. The strawman syntax is inheritance-like syntax. Maybe something else is better. But the idea is run the metaclass value and then run this, because this is a more specific form of a value. So value already gives it copy constructors and no virtual functions and those kinds of things. And what we're going to say is basic enum is a type that, first of all, can't be empty. So we require that the number of variables is greater than 0. That's data members. We require that, here's a cute little trick. If you're wondering, data members, but enums don't have data members. No, but there sure are a lot like a class that has nothing but public constexpr data members, the enumerators. So if you think of enumerators as public constexpr data members, well, let's say all of the variables are, if it's not, doesn't have access, by default it's public, and then we enforce that. If it doesn't have a storage duration, make it constexpr and then enforce that. If it doesn't have a type, set the type to the code I skipped, looks at the type of the first element. And if it's auto, we just pick int. And if it's otherwise, we use its type, the first element. And then we provide the explicit conversion operator and such. So we are composing a metaclass, we're composing the value. So this is a basic enum is a more specific value. We apply defaults, public constexpr, and then enforce them. And we could also enforce that there are no functions, although this particular code doesn't do that. I'm sure you can see exactly how to cut and paste 2 lines to also enforce that there are no functions. And then I can say an enum class, for example, the C++ 11 enum class, is a basic enum where I also add a constexpr block to default the values to one above the previous one unless it was set explicitly. And so then I can write enum class state. Notice it's enum underscore class state. Auto started equals 1, comma waiting, comma stopped. And that is, even syntactically, thanks to Dennis Ritchie making enums look similar to classes, that is already very close to what you actually write with enum space class. Instead you put the base type in as the underlying type as a base with enum class in the language. You say state colon int, say, whereas here you just say int started equals 1, etc. And there's a semicolon at the end because we love semicolons. Semicolons, they rule. And then I can have Scott games. Diamond starts at 9, hearts is 10, spades is 11, clubs is 12, gone is 24, and I can do all my normal enums. If we had had this 30 years ago, would we need a separate enum concept in the standard that's bifurcating our type system? Maybe not. And again, look, no standard ease, and I claim no loss in usability, expressiveness, error quality, or performance, especially runtime performance. Compile time performance, we have to make sure that we get enough. But definitely runtime performance, because all of this happens at compile time. And then, once I have all that, I can easily write a flag enum that simply declares the bitwise operations and has a different constexpr block, which instead of doing +1, does powers of 2 and doesn't let you write any of the values yourself, because it's always powers of 2. And this is just code. The first half is all declarations. It's regular C++ grammar declarations. And then there's a constexpr block of compile time code, which is just regular C++ code, whatever is allowed that we decide is allowed inside a constexpr block. And then I set, using reflection, I reflect on and set the values. And now I've got a flag enum. How many of you have reinvented your own flag enum types? Yes. How many of you have used environments where there are non-portable proprietary flag enum types? Yes. We keep reinventing this. Should we standardize one in the language? There's probably some demand. Should we standardize interface in the language? That's a common thing. There's probably demand. But it'll never happen. It doesn't carry its weight. As a language feature, do we really want to airlift those 18 pages of the C# spec for interface into C++? I mean, we'll get to 2,000 pages that much faster, right? Do we really want that? And how many of them could we afford to add in the language? But if you let people write them as libraries, suddenly they get cheap to add, assuming the language feature bears out. The general underlying language feature of metaclasses that supports it. Now, I actually wrote a bug the first time I wrote this. So first of all, let me point out we have a relationship between basic value. A value is a basic value. A basic enum is a value. And we've got these relationships so you can compose metaclasses. But the first time I wrote this is I actually forgot the XOR. And an OR, of course. Oh, yeah, that's right, XOR. And so what I'm about to claim, many people in the evolution working group in the committee agree with, so this is not just me saying this. I forgot it, so it took me 15 seconds to add it, because I just cut and pasted those two lines and just changed the bar to a caret. Adding in a standardized wording would have taken at least an hour, and if you don't believe me, you haven't been to evolution working group and core. And the answer I've got from committee members who've seen these slides is that universally, you'd never get it through in an hour. Because it's expensive to work with standardese. And with an English specification that tries to say precisely in an imprecise language what a precise language rule ought to do. Code, on the other hand, is precise. Code don't lie. Code compiles. Code unit tests. We love code. Here's another example. A property. This has been proposed to be standardized, but again, one of those things that just has not gotten enough traction to be put into the language, but people keep reinventing. So today I might have a hidden data member int value and provide get and set functions. By the way, disclaimer, are properties the solution to world hunger? Of course not. Can they be overused and abused like a knife? Yes, just like a mugger in an alley can use a knife on you in a way that you do not appreciate. But that doesn't mean you don't want them in the kitchen. You just don't want them lying around on the floor or in the wrong people's hands. So properties, yes, they're overused, but they're still useful. That's why we keep reinventing them. And again, I'll keep harping on the same thing that I keep boring you with because it's important. We C++ programmers already do it. We keep inventing these. .NET, or not .NET, C++CX has them, Qt has them. Every IDE under the sun adds you some support for properties in C++. They're just non-standard. They all work a little differently, but there's a need. But it's something we'd never standardize in the language because it's too expensive and too controversial. I would like to be able to write a property metaclass that is templatized. So think of property as a templated metaclass that takes the type, the underlying type that you want, gives it a value, and if you leave it empty, could even make the forward declaration do this, but if you leave it empty, by default it says, oh look, you didn't define a data member. Here, let me define one for you. You didn't define a get or a set function. Let me define one for you. And so that you get the same thing that's on the right-hand side. Now, property of int, because it is a class that's generated, just property of int value generates a nested class inside my class, which is not the same as the right-hand side. But you might have noticed I am using a metaclass also on my class. I'm calling it, say, class X, extended class. What does it do? Among other things, it iterates and notices any properties and inlines them into the base class so they can refer to each other. So this is how you can, another way to compose the two. And we can default and enforce that you can only write get and set functions. We can enforce that you can write them with conversions, just like the standard std function, that you can, if it's a property of int, that you can write a get that returns something that's convertible from int. You can write a set that takes something convertible to int. Things like that. Very flexible, type safe, but convenient. And you can write all that in your metaclass. And if you want to write a custom one, say string val, your own get and set functions, you can do that, and we can make sure you do it right in the type system. Now, I mentioned Qt uses these. So today in Qt, you write a Qt property macro, and this is just a subset of the features that are available with Qt macros. But you write your value, you use annotations to say, oh, well, these get and set functions relate to that value. And I would like to be able to write it something like the right-hand side instead, and again, have Qt class do all the things that a Qt class needs to do, including treat any nested properties the way that Qt properties ought to be treated, and be able to write this in C++ code instead of putting it through a separate compiler, and still have all the options. I could have a different stored type and a custom getter and setter and still be able to write that myself. But on the right-hand side, I have a pair of braces that define an abstraction, and that's powerful, and they reuse this well-known word. Today, Qt does this with a more complex build chain. You write a header file that includes extensions hidden by macros. You run it through a mock compiler as well as your C++ compiler and combine the results. I would like to just write this as C++ code that goes through my normal straight tool chain. And you can do other things besides properties. For example, signals and slots are another thing that we're currently actively investigating, with trying this out with Qt as one of our examples that we're testing out over the coming year or so. Look, instead of saying signals : void my signal, could I say signal my signal? And then do all the processing for a signal. That's a well-known return type that the QClass metaclass can recognize, for example. But it's not just about Qt. Remember I said everybody and their kid brother framework reinvents properties? Well, so did the Windows team with, over the last decade, their new version of Windows apps. And so C++CX had to support that. Well, you can't talk about properties in portable C++, so we added extensions for that. We decided to do it in the language, so you needed an augmented compiler that took a superset of C++. The good news is you still have a single tool chain. The bad news is it's still not portable, so it still won't work in Clang. And it opens you to accusations of proprietary extensions, but you either support properties and put the information somewhere, or you don't support properties. So this is one approach, is to put it inside an extended C++ compiler. The current C++/WinRT work that Kenny Kerr and colleagues are doing goes a bit back to the COM approach of putting it in a separate middle compiler. So you still have the extra information, but we'll keep it away from the C++ compiler, but we still have a separate compiler. This is much more like the Qt mock model. And I would like to be able to have just my single compiler be able to compile all this, which includes emitting information that's needed by the framework. Qt emits some metadata they need. The Windows team has to emit a WinMD file of Windows metadata. So I have to be able to do some file I/O at compile time as well. Or as a separate build step, I can generate a function that I run as a build step that generates that from the metadata that I reflected over. So how would this look? The general idea, I wouldn't worry about the specifics. The general idea is, look, non-standard, non-portable, complex code. Potentially standard, portable, simpler code. That's the takeaway. And if I say RT interface, that's my generalized opt-in that can say things like, I inherit from inspectable. I must have only public data, public member variables, things like that. And all of my functions that I declare must be, under the covers, transformed so that whatever their actual return type that I declared in the source code was becomes an out parameter and a pointer to that and gets replaced by hresult, because that's what the underlying system needs. All of that is done by a separate compiler today. It would be nice if we could do that transformation by transforming the source to the generated C++ type in C++. One other example, just so you know it's not just about Qt and Windows. I gave a smaller version of this talk about a month ago to a group of physicists, and in particular from CERN at Podio, the Podio project. They do something similar again. They write YAML that gets run through a compiler, and here is their YAML script. They write example hit : that's going to be a type. And then there's a description, an author, and there are some members that look suspiciously member-like, but except that they're a bullet list of text. And from this, they generate, through this YAML script, 5 interrelated classes with a separate code generator. Wouldn't it be nice if they could just say Podio : data type? And then, yes, anything that's string, can we treat that as a constexpr string for your description and author? Your data members, we know what those are. And then we generate those same 5 overlapping and interrelated types from just this one that contains all the information that we have today as a non-C++ script. Can we bring it into the language? There's a new book out. If you haven't already, you run, don't walk, because I think the bookstore sold its last copy yesterday already, but they might be getting more. So thank you to David, to Doug, and to Nico, who is also here today, for writing this very nice book, second edition of C++ templates. And I just had to page through it when I saw it for the first time on Sunday night. And so I took a picture. I love phones. And so I think this is fair use. Sorry, guys. There's this page 495 about the curiously recurring template pattern. You will see in a moment why I flipped straight to that page. The very first thing you might notice about the first 3 lines is that you might call them the curiously recurring template pattern CRTP pattern, because they repeat that whole string in those first 3 lines. But the idea is that you templatize a base class and the derived type gets stuck in as the base parameter. And once you see this, first of all, how many of you have seen or used CRTP? It's one of those acronyms of consonants that we invent because C++ can never have enough of those. NSDMIs, anyone? But there's one question that you should ask yourself about the curiously recurring template pattern. Why do we do it? What's it for? In a nutshell, yell it out, a couple of words. Composition to query the derived class? Yes, so we customize the base class based on the derived class. Sound familiar? Here's an example from the book, slightly cleaned up, of a CRTP equality comparable, again, templatized by its derived type. It exists just to inject the not equals operator into the derived type. And then the derived type says class X colon public equality comparable of me, of X, and passes itself in. Just about line for line. Because CRTP, I'm still going through the exploration, but it seems to me that all the uses I've seen so far of CRTP are doing what metaclasses aim to do in a more general way. You are trying to query something about the derived type and provide something in the base that customizes it. And of course, reflection will only help CRTP do more things. Wouldn't it be nice if we could give a shovel to say it more directly instead of abusing a useful but not designed for it a language feature, which is templates? Here's one other example, and again, very similarly, I don't have the exact syntax yet for ejecting those wrapper functions, but again, it's one for one what we do with metaclasses, and we're doing it already. So some open questions. We have to validate the compile times are going to be good enough. Is this still C++, or are we turning this into Lisp, which could also generate compile time stuff? To the extent that we make sure that we are automating and providing direct support for things we are already doing in C++, we can be sure that yes, we are still C++, that we haven't turned a corner and gone astray somewhere. Will this create divergence? What if n companies define interface? Absolutely. When Bjarne gave us classes, what if a C programmer had said to you, oh darn, but classes, people can write their own data types? That way lies madness. I mean, everybody might write their own string type. True, they did. But classes are still useful, and we could not live without them. And they still have driven a generation of the industry into far larger and productive and scalable systems. So a metaclass is another encapsulation. And how will we debug this? Well, I said in the example, see the compiler debug shape. Yes, we already have generated functions. We already need support for step into generated function. Anything we do for metaclasses will directly help those existing uses we already have. And the way to think about this, a key mindset here, is just go back to always thinking, hey, the idea of metaclasses is the class and struct are the first two metaclasses, and enum and union the third, the second and fourth. But they're just baked into the language. Could I write me some of those using compile time code, please? That's the idea. And notice the keyword already is all over that slide. It's still very C++ because we're already doing these things. They curiously recur. We should ask ourselves why, and then give something direct for it. So recall, abstractions are hiders, and the whole point of the example I gave is that I'm already showing you that yes, we need to expose what is generated, the actual definition. Doing that using constexpr compiler debug is a first step, but it's exactly the kind of thing that debuggers and IDEs will need to do. A last thought on making C++ powerful and simpler. The way you make something bigger but more simple to use is to add abstraction. And there's two kinds of abstraction. One's built into the language, and user-defined ones where the users can make their own word of power. We only have two of those in C++ today, the function and the class. Now, some of you might say, well, that's not right. We have so many features. Templates. But templates parameterize types and functions. They don't encapsulate anything. They don't encapsulate behavior. Overloading, absolutely. Static polymorphism, wonderful. But it doesn't hide anything. It's not an encapsulating user-defined abstraction. Even modules groups things together, and it is an isolation boundary. That's very important. It doesn't encapsulate behavior so much as group it. So it's not creating a new behavioral thing like a class does. All of those are absolutely valid and useful. We want more of them. But I'm hopeful that metaclasses might be the third of those things that actually let users define words of power in a way that simplifies how we use the language. So we want to expand our abstraction vocabulary, use it for everything from enforcing, using reflection and compile-time programming, to enforce coding standards, to write language extensions as library code, and many kinds of them. Then we don't have to wait for new compilers. We can share language features, what would otherwise be language features like property, as a library. And that means we can also take, not all, but at least some of the language feature proposals that are going through committee and perhaps treat them as libraries, which are easier to debug, much less expensive to process, and you don't have to wait as long to get them in your implementations. So remember, all of this is under construction, but I picked this example for a reason. I believe that is the construction in Hyderabad in India of a monorail system. And you'll notice that you know you haven't gone off track when you stay parallel to your original traffic road. The same is true in C++. We can generate all sorts of bridges to nowhere that don't belong in our language. The way we stay rooted and make sure that we're doing things that belong in our language is to make the roads we are already traveling easier, cheaper, more direct, more high bandwidth to travel. If we can find people who are digging with spoons, that gives us the examples and use cases. It demonstrates the need and value of what we're doing. And so I'm trying very hard to stick close to that. If you want to find out more about how some of these things are implemented, see Andrew's talks at 2 o'clock today and at 9 o'clock tomorrow morning. Again, warning, it's not about using them. You won't see examples that are of uses like we did today going through, but you will see what does it take to implement this in Clang? How did he, as he was implementing these things, what did it teach him about how C++ works and how these things need to integrate in? So especially if you have an implementation mindset, check out his talks. We have a couple of minutes left for questions and a couple of microphones. Would anyone like to ask a few questions? And then you can stop me when we're done.
Hello. I think that an important subject matter in your presentation is that the standardese, because it is written in English, doesn't help pretty much anybody. So is it not a good proposition to build a language to specify things into the language so that the specification is code?
So that is a valid approach. Lisp did that, for example. This is, you might view it as somewhat an attempt to that, but there has been no work on a general meta C++ meta language that describes C++. Bjarne has stuck very close to make sure the C++ standard library can be implemented in C++, which is almost entirely true, but not that the whole language can be spec'd. So no, there's been no work in that, but other languages have tried that. It leads to different places.
Hi there. I was listening to your talk and I was a bit skeptical. After all, you're about to give us a very sharp knife here, right? So you had me when you talked about flag enums, because that is very clearly a thing that would be useful to have, but it's kind of very clearly a thing.
The which?
The flag enums.
Mm-hmm.
It's very clearly a thing that is not worth like making it a language feature, but it would be good to have. So I saw like, okay, this could be really useful. What made me a little bit concerned is when you said like, it would be very difficult to agree in the standards committee on what an interface should look like. It's much easier if we have this meta feature so people can define interface. And I just beg you that you still do the work in the standards committee and agree on what an interface and an enum and all that is so that you specify it and you can ship a standards library that comes with them. Because otherwise everyone is going to build them themselves. So you still do the work. It might be easier if you have like a framework for that kind of work.
So let me completely agree with you and clarify something to make sure it's really clear. Just like with classes, very common, and I guess I forgot to say this, very common, widely used metaclasses would also be put in namespace std. Why write interface more than once? Where I was going with that, the reason it wouldn't be standardized is not because of controversy. Property probably would fail because of controversy. Interface wouldn't. But just because, is it really worth its freight? Is it worth 18 pages or whatever of standardese and potentially bifurcating the type system again, as we did with enum, to add it? As a baked-in language feature compiler writers would have to implement, doesn't seem worthwhile. Yes, it's useful, but it's not that useful. Whereas, if I had a general feature like this and I could write it as a 10-line library, I'll bet you dollars to donuts that would sail through Library Evolution Working Group.
Okay, I can see that. It's just like, don't give us the knife if you don't give us like some nicely carved.
Oh, absolutely.
To use with
So,
already, or we will hurt ourselves.
like all other abstractions, we should standardize common ones, and then we can. But then, because it's code, we can have a much better time agreeing on exactly what it should be.
Oh, okay. See, thanks.
Hi. Can you go back to any slides that you are iterating over class member functions?
Can you just ask the question verbally?
Can you go back to any slide which you are iterating over class members?
Yeah, I understood, but I was just thinking of saving the time to go back to a slide. But
Sorry.
Let's see.
Yeah, because I'm
Somewhere around.
any slides that you have a for loop and make something.
How about that one?
Yeah. So I saw you use the syntax all to F column. So this copies the thing generated from a function sequence, right? So it seems that when you are modifying F, the change is directly propagated into the language. But what if I want to have a disjoint copy of the meta object pointed to by F and make changes over there and swap it back?
Yes. So the short answer to your question, well, besides also see Andrew's talk, but the current syntax uses an in-place semantics. That is, I'm modifying my metaclass as if in place. There are good reasons why we're probably going to switch to a source destination syntax where basically the code is the same. But I believe in the current prototype, you would actually say $prototype.functions. So it's another class, and then you would inject each one instead of it having be there. So the structure is the same, but you're right, this has in-place semantics, and that's one of the things we're looking at, saying, is that really the right thing? Or should it be copy from here, generate here? Could lead to clearer code, yes. So we're definitely pursuing that.
Thanks.
Yeah, good observation.
I had a couple of questions, possibly related to that last question. In the literal type example, it talked about generating the make underscore functions as well. But they would be outside the class, or is the intention to be something like friend?
Yes.
Contrasting with the if constexpr, which definitely maintains the scope for good reason.
So all of the examples that I show in the paper and all of the examples that the prototype compiler currently supports, although that's about to change, is transforming one class written in source code to generate one class. Mm-hmm. The pod.io example already goes from 1 to 5. And generating non-members or injecting into enclosing namespaces absolutely is necessary. And so that will be added as well. Because then otherwise you wouldn't be able to do literal value because it requires generating non-member functions as well.
Yeah. So, okay, great. The other question I had was also about literal value. Assuming literal value is clear enough that it would easily go into the standard library of meta classes, would you then consider it likely that we would see things like pair restated in the standard as literal type AB rather than all the standard E's we have now?
So this is all very speculative, but you know, granting for the sake of discussion that this goes anywhere, that it works, that it becomes standardized,
sure,
that you have a standard literal value, then we can have the discussion, as we always do, is can the standard library adopt the new language feature without a breaking change? Because then the standard library vendors would have to think about, well, would this be an ABI break? Maybe for the existing ones, we'll still write them the way we did before, but new things we'll write using the new tool. Perhaps we'll deprecate those ones and then transition people over, or maybe it's not a breaking change at all. We will be careful to write the literal value metaclass so it generates exactly what we have now, and then we can just go do it. That would be the exercise you would get to at that point. That's like 3 or 4 steps, major steps beyond where we are. But that's the kind of thing that we would do and that we do already with other proposals where the standard library is adopting a new language feature.
Thank you.
Peter.
My main question about composability has mostly been answered already by the last 2 questions. And thank you for giving my students the next decade of a lot of interesting work to do.
Thank you, and you're welcome, I think.
Hi. Thank you for a great talk. And to my question, I'm just curious, how far can we go? And how far are we from templates for metaclasses?
Oh, we absolutely need templated metaclasses. So one example that was in these slides is property. So you would define that as template, class T, $class property, because that's how you would say, I want a property of type int. Then you could say property angle int angle my property.
Okay. Thank you.
Yes.
Not that you already don't have enough to do with metaclasses, but have you given any thought to having inheritance of metaclasses? For example, if you're in a company and you want to specify that all classes have an assignment operator, or they all have something which would give you a major or minor version of that class, so everyone in the company could start with that base interface and then create their own interfaces from that?
Yes, and again, so some people will view this as a wonderful thing, and I think it is. Some people will exactly be worried about the bifurcation of company-specific styles. So what I'll point out, using this as an example, is that the way you phrased your question shows your company is in fact already doing this, probably just enforcing it with linters and other kinds of tools, or not enforcing it. So again, it's something we are already doing. Right. We will do it much more rigorously and predictably and correctly and simply if we can just say it in code. Another example that's come up when we were doing like usability studies, one of the things we learned is everybody comes up with a use they could use in their current project for metaclasses, and they're all different. One is for coding guidelines or custom conventions like you have. Another one was that they said in their shop they use a robotics library. It was a machine library. It was a controlled machine, numerically controlled machine. And to use this library, the library required all of your classes had to follow a certain pattern, which right now they do by hand. They forget, then things break and it's hard to debug. Where they could just write the pattern once as a metaclass, they figured they could do it in like 20, 30 lines. And then they'd never have to worry about that problem again. And it would be just, okay, here is the convention in code of what this library requires. So that's probably similar to your example.
Yeah. Thank you.
We probably have time for just one or two more, so let me take one each. Apologies for everybody else who's waiting, but I'll be up here for a bit after.
So how does your compiler.require differ from a static assert?
How does compiler.require differ from static assert? Look at my paper, P0707. There's a discussion of that in there. The short version is it can be integrated into compiler error messages. You have some usability benefits that you don't have with static assert. For example, in a metaclass, you can write that. What's the example I'm trying to think of? Let's say you want to try to, if I'm remembering the example on the fly right, you're trying to ensure that I'm writing a container like vector of t, and I want to be copyable, not just movable, if t is copyable, not movable. Where do you write that static assert today? Because you can't write it inside the instantiation. Sometimes you can write that inside the instantiation of vector, but you have to write it after vector's been instantiated, and some of these you have to write outside the class today with static assert, whereas a metaclass would give you a nice clean place to put it. I might have misremembered the particular compelling example, but that's the one I remembered off the top of my head, is when you can't write it, the static assert in that location today.
All right, thanks.
Hi. I guess I had mixed feelings of your discussion on CRTP. I'm glad that you mentioned it, but I was sorry that you mentioned it so late. So in all the code comparisons, on the left you have 17 code, on the right you have the metaclass code, and it looks much nicer. But reflection is a precondition, and CRTP already exists in the language. So if we on the left instead took CRTP, like greatly enhanced by reflection and maybe also injection, I mean, so you kind of framed it as, oh, like we're not going to need CRTP anymore. It's not meant for that. I think the not meant for that ship has sailed in C++ a long time ago. But we use CRTP, it works, so won't CRTP plus reflection and maybe injection cover almost all of the examples, most of what we want to use metaclasses for, and leave metaclasses not able to carry their own weight as a new feature?
Excellent question to end on. CRTP is a spoon. We are digging with it. It was never designed for it. It is a glorious hack. Like it works effectively. But it can't do everything. I was careful to say, I think, the recording will tell you whether I'm a liar, that metaclasses let you do a superset, let you do everything CRTP does, I think, of the examples I've seen so far, and more. For example, with CRTP, because of C++'s rules, remember CRTP is the base class. You tell it what the derived class is so it can inspect it and such. So reflection will let you do more CRTP, absolutely. but it will always be doing things in the base class which can be hidden by the things in the derived class. It's not it's not putting them together. It's going to have trouble generating non-member functions. It's going to have trouble generating multiple classes, like the Podio example I gave that the CERN people are doing, where from one script they are creating 5 classes. You can do, but you'll need 5 CRTPs and you'll need to invoke them all every time. You can't just say, Podio data type this, and then generate all the things. So I'm not trying to diss CRTP. It has been very useful. That's why it's curiously recurring. That's why it's recurring. It's curious because it's not what templates were meant for, and it seems like that we're trying to say something indirectly, and we would like a way to say it directly. So I'm trying to address mostly the curious part. It's absolutely recurring, and it will be even more useful with injection and with reflection, but it still won't be able to do the full generality of things because it just wasn't designed for that. It's a coding pattern or idiom, not a language feature in its own right that we can make do what we want and make general. So I'll hang around for a few more. Thank you very much for coming. Enjoy your lunch and then the lightning talk sessions.
Bash Films can shoot your event with multiple cameras, link to presentation slides, add titles, and edit your event live for a full broadcast experience.
How is this even working? So this is actually a more interesting program to look at in a lot of ways. So let's profile it. Give it a little bit of time to do a profile for us. Let's see exactly what it is that's making this faster or slower based on the different inputs. I mean, you can really gain a lot of insight by actually looking at the profile like this.
I worked at Sesame Street. I got brought on to be a writer's assistant on a show called Sesame Street English, which was to teach English to kids in China and Japan. It seems very simple, the shows that they put together, but it's actually really hard to design a show that is not only for young kids, but also the parents.
Confession like this is therapeutic. I hope you all get something out of this, but if you don't, the therapy will have been good for me, so thank you. 7 years ago, I was working I wasn't working at Google. It was for my previous employer, which was a large multinational investment bank. I had what was up to that point the worst day of my career.
And then came the anger at ourselves because we knew we were responsible for America's first space disaster. We wrote 2 more words into our vocabulary as mission controllers: tough and competent. Tough meaning we will never again shirk from our responsibilities because we are forever accountable for what we do. Competent will never again take anything for granted. We will never stop learning. From now on, the teams in mission control will be perfect because as a team, we must never fail.
One other thing. We're all in a very fortunate position. We've been very lucky in our lives and so forth. And I think as part of the mission, it's also good sometimes to take that fortune and give back. To make sure that you take this platform and use it towards worthy causes. That's good karma. That's good stuff in the universe.
We understand that your event will have needs that are specific to your organization. Please email or call us directly to discuss your particular event. We look forward to discussing your goals and helping make your event a success.